Thanks, Mike. So I'm Hassan Hamdar. I'm a Senior Program Manager of Event Analysis for SERC Reliability. And we wanted to talk to you about an event that happened actually in the SERC footprint. It's kind of bordering SERC RF area under one of the large ISO RTOs. So there is actually a document posted on the NERC website on this. If you'd like a little bit more information and you'd like some specific actions and things to look for, the link is posted here, and I believe this presentation will be posted after the webinar today. Next slide. So you can go ahead and click the next one. So this is just a simple one-line diagram to kind of show this system where this occurred. So as you see there, we have a fault at substation A, and it looks like it clears normally between station A and station B, and there appears after these breakers open, there appears to be no fault on the system. Next slide. So as a result of this, we noticed, system operators noticed that there was a large reduction in load, and they started trying to investigate why. And this was actually the way we found out about it, the ERO found out about it, SERC and NERC in the regions. This was actually reported through an OE 417 as a loss of load. So from the bulk electric side, it looked like we just dropped a bunch of load, right? Next slide. So when we looked at the overall load curve for the ISO RTO, we were able to discern that it was about 1,500 megawatts of load loss, almost instantaneously, very, very close to the time of the initial fault on the system. Next slide. So we quickly realized, and the entity really quickly realized, that this was almost all exclusively data center load. I said almost all. This was exclusively data center load. It was about 25 to 30 substations, as you saw in that previous simple one-line diagram, and it involved about 60 individual data centers load points. They range, there's a big range. This was kind of a big takeaway for us was you can see this redacted data here on the screen is actually showing you load, data center loads and the size of those loads. They range from anywhere to 2 megawatts to 85 megawatts. So there's a big variance in these things. I know Molly hit on a lot of that being in the PJM load pocket. We've really seen quite a bit of this load, and there's some differences here, but there's also some similarities, and we'll touch on that. Next slide. So after the fault clears and we lose the load, we do see a rise in frequency, which is not something we're used to. We're used to seeing dips in frequency after events, right? So this is different, where we're losing load and not generation. Our typical MO is you'd lose generation, you'd see a dip in frequency. Well, in this case, we didn't lose any generation and we lost load, which gives you a slight spike in frequency. That being said, it was only 60.047, so it was fairly manageable at this point. So this is kind of a very zoomed in scale on frequency, just to give you an idea of what was going on. Next slide. At the same time, when we had a loss of load, high frequency, also coupled with that is high voltage, right? Because you have lower load, you have higher voltage. Low load, high generation creates high voltage. But it was below the 10% or 1.1 per unit. So 10%, as we all know, in system operations, 10% during emergencies. And in this case, you could kind of consider it was an emergency. Operators did act to remove a 230 kV capacitor bank and that helped reduce voltage and kind of got them back on schedule. So next slide, Rich will take over on here and we'll run through the analysis.
All right, Hassan, thank you.
Right. Thanks, Hassan. So once we identified that it was exclusively data center load, then we kind of start wondering so why did that load drop off the system? So we and I guess I myself have a kind of a mental model of what a data center load would look like and kind of what their architecture might be. I don't know how many people are on the phone today that might be familiar, but if you're from a utility, every utility has like a mini data center, right? And the mini data center is really their EMS system and their control center. And so from that experience, we kind of have this mental model of what their architecture looks like. And their architecture looks, as you can see on the screen here, is that typically you'll have a transfer switch that has two sources to it. In this case, you can see we've got a AC source on the left-hand side coming from the grid, and then we have a backup generator. Typically they're a diesel generator, but you have a backup generator that's a source to the transfer switch. And so normally the transfer switch is sourced off of the grid or off the utility. And then basically the transfer switch feeds a UPS device. And these are very large UPS devices. They're very, very similar to the UPS that you might stick under your desk, that you have your PC plugged into. But these are on a lot larger scale. These are like 3 megawatt type size of UPSs typically. They have very large battery banks that are external to the UPS, typically like a 130 volt DC battery bank is kind of a common voltage they use. And anyway, then that UPS has that battery bank, and that's actually what provides the uninterruptible power and feeds the critical load. And you can see the critical load in this case is depicted as server load that's on one feeder that might be, or one distribution type of system that feeds that server load. So when we look at this system, what we would anticipate is that if I had a disturbance on the system that resulted in a very low voltage for a very short period of time, right? As Hassan mentioned, that fault was cleared normally, which means that fault was actually cleared in less than 4 cycles. What my mental model would be of how that load would react is that during that very short period of time that the voltage is very, very low, I would expect that the UPS would basically kick in and it would serve the server load. And so I would see on the electrical grid side, I would see a very short duration of a reduction in power, or load consumption. And then as soon as I clear that fault, like in 4 cycles, I would expect that the UPS would then go back to the grid for its source of power, transition off of the battery, and go back to its pre-disturbance level. So I would expect to see like a very short duration of load loss from the grid, and then return as soon as we restore voltage and clear that fault. So I think we can go to the next slide, Mike.
All right.
So what we see in the load chart from as Hassan mentioned, from the RTO ISO, what we see in the load chart is we see that 1500 megawatt load loss, but then we see that the load did not come back instantaneously. So what that says is that the mental model that I had on what I was expecting how the load would respond, that didn't happen in this case. Because, as I said, if you look at the blue chart there, that load was gone for 3, 4, 5, maybe even 6 hours before it came back to its pre-disturbance type load levels. So next slide, Mike. So what does that tell us? Well, that tells us that something else happened. that something else happened in this model, in this architecture design that I have in my mind. Something else had to happen. So what was that something else that happened? Well, in order to figure that out, we can go to the next slide, please. In order to figure that out, we really need to talk to the data center load owner operators, right? And so we were very, very fortunate in that we were able to get in contact with a group called the Data Center Coalition. And the Data Center Coalition is it's kind of a membership group of data center owners. And a lot of you might be familiar with in the way that I try to describe it is it's very similar to what EEI, Edison Electric Institute, is to the investor-owned utilities. It's very similar to that, except it's for the data center owners. And but the real value we got out of that is in conversation with the Data Center Coalition, we were able to get in contact with the actual electrical engineers that design and operate these data centers for the big data center guys. We could call them the big four, I guess you could say, maybe the big six. But at the end of the day, we were able to have a few phone calls with those guys, and they gave us really great information on the protection and control systems and the design of their systems. And at the end of the day, we were just able to really garner a lot of information. And you can see there's a sampling of some of the information we got from them that we felt was, pretty critical and important information. But if we go to the next slide, Mike, the one thing that I think, at least for this event, the real gold nugget that we got out of that conversation with them is that one bullet item there that says they will lock out after a number of events in a specified period of time. And truly what we found, a little more detail into that, is that a real typical kind of protection/control scheme that the data centers employ is that if they see 3 disturbances, or in other words, if they see 3 like low voltage excursions within a certain period of time, they'll lock out from the grid. And a typical time frame is about 1 minute. So in other words, if they see 3 voltage disturbances within approximately 1 minute or 60 seconds of time, they will they'll transfer their load off the system. In that previous slide where we had the UPS design, they'll transfer their load to their backup generator, and they'll stay there and they won't come back. So when Hassan and I, when we went through this event, we didn't quite tell you the whole story. So we can go to the next slide, Mike. And the rest of the story is that we did have a fault on a 230 transmission line, and the protection did detect that fault and it did clear it properly. However, the fault, the source of the fault on the 230 transmission line was actually a failed lightning arrestor. And so that failed lightning arrestor presents a permanent fault, right? Since the lightning arrestor has failed, we've got a piece of equipment, and that line will be faulted until we remove that lightning arrestor and replace it, is typically what people do. But until you disconnect that failed lightning arrestor from the line, that fault will be on the line. So what that really means is that we have the initial fault when the lightning arrestor fails, and then in practically, most instances, we have what we call automatic reclosing on transmission lines. So we have a scheme that will automatically, if I see a fault, I detect the fault, and I trip the circuit breaker to de-energize the line. After a period of time, I'll automatically reclose that circuit breaker because most of our faults are temporary in nature. They're transient faults. So if we clear the fault, we wait a little bit of time, and then we re-energize, the fault will be gone because it could be a bird, a tree limb. It could be a lightning strike where an insulator flashes over. But you know, the majority of our faults are temporary, so we employ this auto reclosing scheme to just automatically reinsert the line back into service. So in this case, the entity, we have a permanent fault, so the fault's not temporary. So we go through the entire reclose sequence, and then eventually we lock the transmission line out, and we quit trying to re-energize it again. Well, what that resulted in, based on the entity's reclosing scheme, automatic reclosing scheme on this line, we actually we created 6 voltage dips or voltage disturbances on the system in about 82 seconds. But we also, if we look a little closer, the first 3 dips on the left-hand side of the screen, those all occurred within about a little over 20 seconds, 25 seconds. So we basically gave the data centers 3 voltage dips within about 25 seconds. So they told us that they would lock out after 3 disturbances within 60 seconds. So we definitely did that. So we can go to the next slide, Mike. So actually, the phrase that I've actually coined to try to describe that and try to burn it in everybody's memory is 3 strikes you're out, right? That's a real common term we all kind of know about. We've all grown up with that phrase, and at the end of the day, that's kind of the control and protection scheme that the data centers employ. Is that they're going to look. I'm looking at the grid, and if I see 3 disturbances in a short period of time, less than 60 seconds, my confidence in the grid kind of falters at that point in time, and the data centers go, you know, I'm going to go to my backup generator because I'm losing confidence in the grid, and I'm going to go to my backup generator, and I'm going to stay there until I get confidence back that the grid is actually going to be secure. So, like I said earlier, when I referred to that as a gold nugget, that finding was a gold nugget. In the case of this event, that was the most significant contributor to that 1,500 megawatt loss of load, was that 3 strikes you're out kind of protection scheme. So now we can go to the next slide, Mike. So why are we concerned about this? Well, I don't think I even have to tell everybody why we're concerned about it after Molly's presentation, right? A great segue into this. You know, you guys saw all of those graphs about, you know, the predictions on where data center load is going. And 1,500 megawatt loss of load in July of 2024, how much might that be in July of 2025? You know, how much might that be? We saw that graph where we kind of hit the knee of that curve, right? In 2030, is that 1,500 going to be 15,000 maybe megawatts of load loss? So at the end of the day, that's really what our concern is. So we can go to the next slide, Mike. So what are our next steps? Well, one of the next steps is that what we're doing today, actually, right? So what we're doing today is we're just trying to heighten the industry awareness of this issue, of this controlled protection scheme that data centers employ, and basically just try to make sure that everybody is aware. Everybody is aware that this is out there, and it's, you know, if you have a high possibility of experiencing this same type of an event, and you might want to be thinking about it, right? Is it going to be a problem for me? Do I need to figure out steps to mitigate it? The other thing is, though, is that we, you know, Hassan showed you guys the frequency and the voltage traces that we had from this event. And, you know, they didn't present major problems because, number one, it happened in the Eastern Interconnection, and the Eastern Interconnection is very large. And so 1,500 megawatt load loss in the Eastern Interconnection isn't that significant. But if that 1,500 happened in, say, the Texas or the Texas interconnection, that might be a real different story. 1,500 megawatts is a significant load loss there. So at the end of the day, that's what we have to do is we've got to go and analyze now, because we've never really dealt with large blocks of load loss, right? We've always dealt with large generation losses, and we plan for that and we study those, but we really haven't planned and had to deal with large load losses in the past. So that's what we need to do now as an industry. We've got to go and analyze and say, okay, at what level of load loss are we going to have significant problems? And that, as I said before, that'll be different for each interconnection. So we kind of need to establish, that bright line that says, if we stay below this, we wouldn't have a problem. But if we go above that with our current system and our current practices, that could very well be a problem. And then once we analyze that and determine, what that risk, what the risk is, how much of a risk it is, then we have to go and decide, okay, how are we going to mitigate that? Do we need to change some standards? Do we need to change registration criteria in order to try to mitigate these things if we do detect that the risk is too high? So those are all the questions that we have. And then the last bullet item on there is the one. So NERC has created a large load task force. It sits under our Reliability and Security Technical Committee, RSTC. And so basically at the end of the day, we've kind of tasked that task force with doing that analysis and making determinations as to whether we need to make changes to standards or not. So that large load task force is the body that has that kind of large challenge in front of them, and they're off and running. And I would encourage anybody that is interested or impacted by any of this stuff. We encourage everybody to participate and monitor that large load task force, because they're in the process of trying to write white papers and guidelines and things like that now. And so we need all input in there. And I would say this, I'll make the one big plug today, and that is that we really need the data center owner operators to participate in that. And right now, I would say that we're a little light in that area. So I would really encourage that. So I think next slide, please. I think, is that the last slide, Mike?
Yes. Yes, it is.
Yeah. Okay. That was a whirlwind tour, but hopefully everybody's got a good feeling.
Well, Rich, that's a great presentation. We've got several questions. Some of them are similar, so I'm going to kind of pair those up together a little bit. This first one is around registration of data centers. A couple of questions. One was if these particular load centers were registered, and then the other question is, will data centers have to become registered entities?
Yeah, so the first question is no, none of these data centers that participated in this event were registered. There's no requirement for load, individual load type things like that to register now. And so, one thing that I will say is that I think a tremendous, and I shouldn't even say it's an advantage, I think that it's a necessity. And whether or not we have to register the loads and create NERC requirements for it, I think that we can, have some discussion on that. But the real point that I'm trying to make is that a critical piece in all of this is that the interconnecting utility has to have a good model, or basically has to have good information to know how the load is going to respond. And not really just in response to disturbances on the system. While they do have to have that, in addition to that, they're going to have just a really good sense of what the normal load variation is. And so typically where that comes, I'm a transmission guy, so for me, where that kind of comes down to is that I need to have a good model of the load that's connecting to the system so that I can study that. And we've all seen that. That's really right now, that's where we're in the heart of trying to mitigate and resolve all of the inverter-based resource issues. It's the exact same problem. We have to have a good model of the generation resources so we know how they're going to perform and respond to disturbances. And now, because these data center type loads, or these loads that are getting so large, they can have such a large, they can have a significant impact on the system. We're going to have accurate models of them so we can study what their impact to the system is during disturbances also. So I will say that I think that's the area that we have to start at, and we've got to ensure that we have those good models. Now, if it's, via standards and registration, or if it's via interconnection requirements, I think that's the discussion we have to have. So hopefully that answered that question.
Rich, I think it did. The next two are kind of paired up as well. I think you've already kind of answered this first one, which was, do we need better load modeling for large loads so that we can stay? I think you've already really answered that. And the one that kind of pairs with that is from your conversations with the load centers, the distribution centers. Did their electrical engineers give you any idea as to how sensitive those loads were? Like, did they give you we know it was 3 strikes you're out, we know it was a voltage dip, but did they give you a sense of the percentage of voltage dip that would trigger that response?
That's a great question, Mike. And if I could ask you to scroll up to slide 14, I think it is. Let's go back
Probably
down.
this one.
No, back down some more. Holy cow, those
right.
have got, I just noticed those have really funny numbers on them, don't they?
Sorry.
Anyway, go down a couple more here. I think the next one, that one right there, that's the great one.
All right.
So the answer to that question lies in this, and I apologize, it's kind of a small picture, we didn't show it. But the thing with computer equipment, a few years back, the computer equipment, they had an organization that was called CBEM, and it stood for Computer-Based Equipment Manufacturers. And they had these Sabima curves, they were called. And that's what that really small curve is up at the top in the middle. And then if you go down to the little bigger one now, down below, where you see this prohibited region, class 1 dynamic output, what they have now is they've changed the name of those curves, and they call them ITIC curves now. And I apologize, off the top of my head, I can't remember what ITIC stands for. But then there's also an international, this IEC 62040, that have created curves. And basically that's what those curves show. And once again, I apologize because I know it's a little bit of an eye chart, so you can't really see them. But that's actually what is defining the sensitivity. And if you look at that the red lines on that chart, and it says class 1 dynamic output, that's like the most sensitive, the most voltage sensitive that the loads would be, is if they adhere to this class 1 curve, which is stipulated in the IEC documentation. And what the data center people told us is that a majority of the new data centers being built will be built to that spec, that class 1 dynamic spec. Now, what I can tell you, if the voltage goes outside of 0.9, they will disappear very, very quickly. They are very voltage sensitive. And what I can tell you is that that's like the most sensitive. I'm looking for another word, but it's not coming to me. But that's the most sensitive. The least sensitive even is a voltage. If they see a voltage in the range of 0.7 per unit for less than 2 cycles, they will go to UPS at that point in time. So hopefully that gives you a little bit of an idea, and maybe it gives you some other places to go look so you can get more information. Look for that IEC 62040. But at the end of the day, hopefully that gives you a little bit of a sense of how sensitive they are, because they are very sensitive.
Yeah, Rich, I think that's helpful. That 10% dip or 0.9 per unit, if they see that 3 times, then we know it would go, or that 30% dip with a 0.7 per unit seems to be something that would happen to move them over to the uninterruptible power supply, the UPS, very quickly. We've got a couple more that are kind of grouped together. They're kind of very similar questions. The question was, about if they trip off and you lose 1,000 megawatts of load, isn't that equivalent to injecting 1,000 megawatts of power into the system? You're answering yes. And then in parallel with that, the question was, well, what happens when this issue grows to a much larger magnitude? This seems to have been a near miss or a close call. What happens when the magnitude grows to 3,000, 5,000, 10,000 megawatts? What happens then?
Yeah, so that's exactly where our concern lies, right? Is where are we going to have problems that arise from that large of a load loss that are actually going to create big problems for us on the system. So as Hassan, showed you in that one graph, is that, so there's 2 things that happen when we, and that's a great way, the previous person, is if we have a large loss of load, that's the equivalent of a large injection of extra resources on the system, right? So the 2 things that happen, physically on the system is that the frequency will go very high and the voltage will go very high. And so at the end of the day, what we're concerned with is at what magnitude of load rejection causes a frequency that's high enough that could present problems, that could present reliability problems on the system, such as maybe widespread tripping of resources because we're in this very large over frequency condition. So then you could go from a very large over frequency to a very large under frequency, and that kind of thing. Then, and of course, the second thing was the voltage, right? Is that if we reject enough load that we have an instantaneous over voltage of greater than 1.1 per unit, that causes a lot of problems on the system that you want to avoid. And so at the end of the day, those are the things that we have to study and analyze and determine where that level is that's going to present those problems. And then we have to avoid that much load loss. So we avoid those problems. Hopefully that answers that.
Well, Rich, thank you. One last question. I know we're about 10 minutes over, and I appreciate you sticking with us and with our listeners, but this will be the last question we'll throw at you today. What about the tail end of this event when loads come back? Is there any concern that as this expands in magnitude, is there any concern about how the loads may come back on either suddenly or at unpredictable times?
That's again, that is an absolutely great question. Hassan and I have talked about this at length many times, and that in my opinion, and I believe Hassan agrees with me, that is as important as the load loss, right? And so right. What we've encouraged, and we mentioned this in the report that Hassan mentioned to you also, but what we're encouraging is that transmission entities, balancing authorities, ensure that you have in your interconnection agreements with these very large loads that you have a controlled plan on how to reconnect load after it leaves the system, because you have to reconnect that load in a controlled manner so that the balancing authority can ramp generation up appropriately to match the load ramp up. And so anyway, that's, like I said, it's in the report, but it's a very critical piece of this, is that we have to be able to control reconnection of that load. And it, you know, we're having discussions with ERCOT right now, and I apologize, Mike. I just realized I got to throw this last little tidbit in. So in ERCOT, a much smaller interconnection, they're very, very interested in that type of thing. And so we're actually in the process of doing a second report based on the ERCOT interconnection with some crypto. Rather than data center load, it'll be Bitcoin mining or cryptocurrency mining, I guess is how we refer to it, blockchain mining. Anyway, ERCOT has experienced some loss of that load. And we believe that that load responds a little differently than actual data center type load. And so at the end of the day, we're working with ERCOT, and we're going to write a second report on some events that have happened down there. And we'll talk probably more about that reconnection of load, because, you know, if you go away and then you come back very quickly once the fault's cleared, that's okay. But if you go away and then you're gone for a few minutes and then you come back very quick, you know, with your whole load, that's a real problem for the BA. So at the end of the day, you've got to have those type of procedures in place where you control that load coming back. So anyway, hopefully that answers that.
It does.
Hey, Mike.
Yes,
Mike,
Hassan?
I'd like to just, yeah, so I'd like to just point out, you know, I think you've heard Rich say interconnection agreements a few times here. There was the question on standards and requirements, and that's come up a few times for us. And what I'd like to remind folks is what we're doing right now is kind of outreach. I mean, we've got what we've got out there now, but we see that there's a lot more coming. And this is all about getting this information out there to make sure folks are communicating as these new data centers are being integrated into the bulk electric system to say, hey, wait a second, what are you going to do? What are you going to ride through? What are your requirements of the bulk electric system? And here's what the requirements of the bulk electric system are of the load that's coming on. Because this is a new world. It's not something that we've dealt with before, right? The other thing I wanted to mention, the system operator conference that you pointed out, the SERC system operator conference, this is on the agenda. So there'll be a little bit more in-depth discussion there if folks would like to. That is an in-person attendance, and you can find that on the SERC website. So just kind of look at this from a little bit different perspective. Look at it from, this is something that we're kind of putting out there for folks to look more for. What are we bringing on the system? AI also brings more difficulties in their own specific nuances.